Okay, so hi everybody. Thanks for listening in. So today's recording is about telescopes, which is basically how we sense the light from different objects, especially astronomical ones. We've talked about how much information can be encoded in the light an object produces, but that information is only accessible if we can detect it. And astronomical telescopes are the way we do that. And what I want to try and explain today is what are the limitations of these pieces of engineering. These are great tools, especially the ones that are out in space, like the Hubble telescope shown here, but they are limited. And this is related to certain kind of fundamental questions people have about telescopes. It's like, with all these great telescopes, why don't we have really clear pictures of the planets and orbiting other stars, or even just other stars? And this is related to basic aspects of how telescopes work that I want to talk about today. So, what we're going to start off with is trying to address this question of why don't we have high resolution pictures of other stars? Now, part of the answer to this has to do with the fact that stars are very far away. And this affects how big they appear to be to us on the sky. Remember, we've already talked about how even though the sun and the moon are very different in their physical size, the sun is about 400 times bigger than the moon, they appear to be the same size to us because the sun is 400 times further away. This applies to all astronomical objects and has major implications for how big they appear to be. To choose another example where the difference in distances is even more extreme, it's worthwhile to consider, say, Pluto, the object in the outer skirts of our own solar system, and the moon. In practice, these objects are not that different in size. The moon's diameter is about 3,500 kilometers. Pluto's a little bit smaller, but it's still 2,400 kilometers. These are comparable in size. But Pluto is 10,000 times further away, which means it appears 10,000 times smaller than the moon. So if this was a proper image of the moon, the Pluto would be a single pixel on this image. So it's much harder to capture details. In fact, this is a picture from the Hubble Space Telescope, which is one of the best telescopes for looking at Pluto. And you can see that in this image, Pluto is barely resolved. There's maybe, you can see parts of it are darker than other parts, but you're not seeing nearly the amount of detail you're seeing in the moon. And that's simply because it's that much smaller. And the thing is, Pluto's in our own solar system. Other astronomical objects are even further away. For example, Alpha Centauri. This is, again, the closest star, the one that should be easiest to take pictures of. And in fact, you might even think it would help because stars are enormous compared to objects like Pluto. In fact, Alpha Centauri is about 800 times bigger than Pluto physically. But Alpha Centauri is also 8,000 times further away. So that means that Pluto is 10 times larger on the sky compared to Alpha Centauri. So to us, the image of Pluto is 10 times bigger than the image of Alpha Centauri. So if this is what Hubble can see for Pluto, we're now talking about a single pixel for Alpha Centauri. And things just get worse from there because other stars are even further away and other galaxies are further away still. Now, just to pointed out, we do have pretty pictures of galaxies. This is an example, and you can find them all over the place. The thing is, though, this is not a picture of individual objects. The stars inside this are these little points of light. This is a system of many, many stars, and it's an enormous system, which is why we can see it. But if we were trying to get data on an individual star in another galaxy, that is extremely challenging and often almost impossible, at least resolving them. Now, I could, in the past, just say that and move on, but it's important to note that we do now have an actual picture of a particular object in another galaxy. This is the galaxy M87, and in this galaxy, in the middle of it, is a gigantic black hole. Now, this black hole is particularly large. It is larger than our own solar system, as we already talked about. So it's 20,000 times bigger than a typical star. But getting this picture was a major feat of astronomical image processing because this thing is really far away. It's over 10 million times further away than the nearer stars, which means that this ring, which is what we're seeing here, is 200 to 400 times smaller on the sky than Alpha Centauri is. This is one of the reasons that a lot of astronomers were impressed by this picture. It is ridiculously high resolution. To give you, again, a kind of impression of this, this is showing the relative sizes on the sky of Pluto, shown here, Alpha Centauri, shown here, and the black hole in the middle of the galaxy M87, which is barely showing up as a dot. So in order to see things like this black hole or other stars, you need a telescope with an extremely high spatial resolution, something that is able to see very fine details. Now, you might say, well, why don't we just get telescopes that can do that? Our ability to resolve fine details on the sky is limited. We can't see infinitely sharp details. And that's for a very fundamental reason. It's not just that it's a hard thing to do, it's a very, very hard thing to do. And it's basically down to some very fundamental aspects of optics. Now, optics is an area of physics which deals with the detection of light. Now, any optical instrument, anything that gathers and detects light, can be broken down into two basic pieces. You have something that detects light, that is, converts light into some other signal, and something that gathers that light. Now, our eyes are an example of an optical instrument. We have a retina in the back of our eyes that converts light into signals that our brains can process. In front of that retina is a lens that focuses light at different locations on the retina. Any other instrument, a camera, a telescope, a microscope, has the same basic components. You have a camera, usually now a piece of electronics that converts brightness into electrical signals, and you have various mirrors and lenses that gather the light. Now, the reason we have this second component, these mirrors and lenses, is because if you just had the detector, you wouldn't be able to distinguish where the light is coming from. This can be illustrated with a simple cartoon example. Let's say you could take the detector out of your cell phone camera and just put it out in air. This thing detects light. It turns it into brightness signals. But you can't use it to make images because there's no way to figure out where that light came from. So for example, we have a red star and a blue star. They're just color different for the sake of clarity here. The light from the red star can reach every point on this detector. The light from the blue star can reach every point on this detector. As far as the detector is concerned, it's just getting light. It doesn't know which of these two sources is producing it. If you want to distinguish things, you need that second optical element. Now, the simplest way to do this, and one that actually works, is you just put a sheet of something opaque in front of the detector and punch a small hole in it. If you have a small hole in this region, then the light from the red star can only get to this part of the detector, otherwise it's blocked. The light from the blue star can only get to this part of the detector, otherwise it is blocked. This works. This is what's called a pinhole camera, and it is the simplest way to produce an image on your detector. Now you can say, well, if I see signal here, it's due to a source down here. If I see a signal down here, it's due to a source up here. And this can work. And if any of you guys were able to experience the eclipse a few years ago, one of the weird things that happens is exactly this. If you look at shadows, they start looking weird. The reason they look weird is every little hole in the shadow is providing an image of the sun. When the sun is being partially blocked by the moon, those shadows start turning into a bunch of little crescents. So this is the simplest way to do it, but it is highly inefficient because you're basically blocking most of the light that could have hit your detector and basically giving it up. So this isn't great. What mirrors and lenses allow you to do is take the light from these two sources that are going over a finite region in space and having all of that light focused to a particular point on a detector. So this is a case with a lens, but you can do the same thing with mirrors. The light from this blue star, regardless of what direction it hits the lens on, gets focused to this point in the detector. The light from the red star gets focused to this point in the detector. So this is more efficient. You're now taking light from a broader range and focusing it onto one place in the detector. So again, you can now say anything that appears here is from this source, anything that appears here is from this source. Great. But there's a limitation to how well you can separate these two sources. And that limitation is what is referred to as a resolution limit. There is a limit to how well you can separate the light from two closely spaced sources. Now, I want to distinguish a couple of things here, which get mixed up occasionally. It is resolution versus magnification. Resolution is set by what kind of details you can observe. Magnification is set by how big the image is. So for example, this is a blurry picture of Mars that I just created in software. It is a small blurry picture of Mars. If you increase the magnification, you turn a small blurry picture of Mars into a big blurry picture of Mars, but you're not seeing any more detail here. Magnification does not help you see detail. Resolution is the smallest thing you can see. So if you increase the resolution, this blurry image becomes a sharper image. So what really matters if we want to see details on a planet or structure on a distant star, it's resolution. And resolution is limited. And it is limited by some fundamental properties of light. The fundamental property of light that's most relevant is the fact that light is a wave. It's an oscillation. So that has implications for how light propagates once it gets constricted. For example, this is just a graphic showing a wave consisting of red and blue bands that is coming onto a wall here and then propagating through it. Now, there's a small hole in the wall, so the light partially gets through. But what happens is that light doesn't just come straight through the hole, it starts to spread. This is a process known as diffraction, and it occurs because these light waves do not like to have sharp edges. So when there is a hole they have to pass through, they naturally spread. This is a problem for creating images because it means if you have a hole, the light coming through that hole spreads out. So the light from this source doesn't just hit this part of the detector, it hits this entire region of the detector. Similarly, the blue star light doesn't just hit this part of the detector, it hits a region of finite range. Now, if these two things are close to each other, those two sprays of light will start to overlap and make it difficult to distinguish. Now, this is a problem with a simple hole camera, but it also occurs with any optical element because anything like a lens or a mirror is effectively a modified hole. The lens is only focusing light from a finite region. So this corresponds to a hole in a plane that is marked here with a line. Now, it modifies the hole somewhat, but this spreading still occurs. The light from this star from the red star gets spread over a finite range. The light from the blue star gets spread over a finite range. So even in actual real optical instruments, this is going to happen, and it's going to cause problems. The issue is the amount by which the light spreads is basically set by the size of the hole that the wave is traveling through. These are two different simulations, again, showing a wave going through a hole. In this case, it's a small hole. You can see the light coming through just this little region, and you can see it spreads quite a bit. If you have a wider hole, the light spreads less. It still spreads a bit, but you can see it coming through mostly in the direction that you want. The actual degree to which the light spreads is set by the ratio of the wavelength of the light to the size of the hole, the diameter. This means that there is a fundamental limit to whether you can distinguish the light from red versus blue, which is set by the ratio of the wavelength of the light to the diameter of the thing the light is passing through, which is basically the first lens or the first mirror of the telescope. So just to give you a sense of that, let's take a bunch of looks at what Mars would look like through different optical instruments. This is just a pretty view of Mars from an orbiting spacecraft. So it's basically as good a resolution as you can get. We're going to pretend, for the sake of argument, that Mars is about 75 million kilometers away, which is basically roughly how close Mars gets to us. So this is the best picture of Mars you could probably get. What does this look like to different optical instruments due to this smearing due to diffraction? Well, it depends on the size of the aperture of that instrument. What is the hole the light comes through? To start with, consider your eye. All of the light reaching the circuitry of your eye goes through your pupil, which is typically less than a centimeter across. So you have a fairly small hole. Now, we'll also say, let's just say we're going to talk about wavelengths around 500 nanometers, which is typical of light, just to get a rough sense. So if you look at this with your eye, the resolution does this. That diffraction spreads it out over a region that's large compared to the size of Mars. So with your eye, you cannot resolve details on Mars. The resolution limit, the smallest thing you can see, is 22,000 kilometers, which is bigger than Mars itself. So instead of seeing surface details, you just see a fuzzy red dot. Now, you can do better using optical instruments, which have larger diameter apertures. The next most logical thing is a pair of binoculars. Binoculars typically have an aperture that's maybe 5 to 10 centimeters across, so maybe 10 times the size of the pupils in your eye. That improves your resolution dramatically. Through binoculars, you could see something roughly like this. You could start to resolve structures about 900 kilometers across. Now, it's still blurry, but you're beginning to be able to see dark patches and bright patches. And through even small telescopes, you can see these things. If you go to bigger telescopes, say things like the Jewett Observatory or even the bigger telescope in our own observatory, you can improve the resolution even further. You can start to see some of the details of those dark and bright regions. Now, and if you make your telescope even bigger, you can potentially do better. Although in that case, blurring effects from other things like the atmosphere start to come into play. Okay? So this is one of the reasons why having a large telescope is helpful. It allows you to start to see fine details. Now, the thing, though, to make it clear is what matters is the width of the telescope, its diameter, not how long it is. There are different types of telescopes which have very different lengths. That's not critical for the resolution. For example, many early telescopes are what are called refractors. They use lenses to focus the light, just like our eyes do. There's a limit to how much you can bend the light with a lens. And that makes the tube of the telescope very long. This is an example of one of the largest telescopes around. It's Yerkes Observatory in Wisconsin. There is a 40-inch diameter lens up here, and that focuses the light down here, and you can see a person for scale. So this is a really big telescope. This is but this isn't the kind of thing people use much anymore. The more common types of telescopes nowadays are reflectors, which is the one you've been using. These use a mirror to focus the light. And this is an example of a reflecting telescope. It is 1.2 meters across, so its diameter is about the same, but it's much shorter. The reason it's shorter is because you can basically change the curvature of the mirror to move the point where the light's being focused closer in. And again, here's a person for scale. Since these two telescopes have roughly the same diameter, they actually have the same resolving power, even though this looks like it's a much bigger thing and thus much better. The length is not as important as the diameter for resolution. And this is why these reflecting telescopes are much more common now. They're just more compact, they're easier to build, they're easier to maneuver to look at things. And that's why we use them these days. And the thing is, now that you can make a relatively compact scope that has a 1 meter diameter mirror, people can go bigger than that. The bigger telescopes these days get quite large. One of the biggest ones is one you can find in Hawaii. It's called the Keck telescope, which has a primary mirror, the first mirror that it encounters, that is 10 meters across. Here's a person for scale. This entire thing is its mirror. These telescopes have potentially extremely high resolution and also very high sensitivity. Now, people are currently trying to make even bigger telescopes. This is just a graphic showing the variety of giant telescopes that are currently being talked about and being built. The Yerkes Observatory lens is right here. Let's see, where is Keck? The Keck telescope is right here. People are currently talking about making telescopes whose primary mirror, which can be broken into a lot of little mirrors, that are of order 30 meters across. Now, there's one of those that was being built in Hawaii, but due to various issues we'll talk about in class, if people are so interested, is currently on hold. There is also a telescope that is currently being built in Chile called the Extremely Large Telescope, because astronomers really should not be allowed to name things. And people have been talking about, could we make a telescope that is 100 meters across? And of course, they're going to call that the Overwhelmingly Large Telescope. So people really want to make big telescopes. And part of that is due to resolution, the more detail. But there's another big benefit to making your telescopes big, and that's sensitivity. The thing is, if you have a telescope that is bigger, it is gathering more light. A 10-meter telescope gathers 100 times more light than a 1-meter telescope. That means you just get more information. You get more light, which allows you to see fainter objects. It also is extremely good when you're looking at spectra, because when you look at spectra, you need to split up the light into its different wavelengths. And you can partition that light more finely if you have more of it. So these are reasons people are going to building larger and larger telescopes. Now, everything I've just said has focused on telescopes in optical wavelengths or visible light. And part of that is understandable because that's what we're used to seeing. But remember, light is just one type of electromagnetic wave. There is UV light, there's infrared light. All of these different types of radiation have different wavelengths and interact differently with different materials. So it's natural to ask, well, wait, what about these other wavelengths? Why aren't we using them? Well, we are. There are telescopes that operate all the way from gamma rays to radio waves. But there are challenges associated with all of these. Now, with regard to resolution, you might say, look at all of this range of wavelengths. If we can go to shorter wavelengths, can't we get to higher resolution? And the short answer is, in principle, yes. The resolution limit is set by the ratio of the wavelength to the diameter. So if you can go to shorter wavelengths, you should be able to see finer details. But there's a problem. And the problem isn't with the telescopes, it's with the fact that if you want to build a telescope on Earth, if you want to look at space, you need to look through Earth's atmosphere. And Earth's atmosphere does not let all wavelengths of light through it. This is a plot showing the degree to which the atmosphere is opaque as a function of wavelength. Here is visible light. Visible light is in a region where our atmosphere is fairly transparent, not perfectly, but reasonably transparent. This is why we can see the stars at night. The atmosphere doesn't block that light. But as we go to shorter wavelengths, the opacity of the atmosphere goes up. It basically blocks all the light in the ultraviolet, X-ray, and gamma rays. Now, in some sense, this is good. Ultraviolet light is not great for living things. So we're protected by the atmosphere. But it does pose a problem to telescopes. The telescopes we have, we can't use ultraviolet, X-ray, or gamma ray telescopes here on Earth. They just can't see through the atmosphere. So that's a problem. Turns out that the atmosphere does kind of restrict what wavelengths we can look at. For example, even at longer wavelengths, there are certain regions in the atmosphere, regions of wavelength we just can't see from Earth because the atmosphere is just too opaque. In the infrared, there are certain wavelengths that are fine. There are other wavelengths that aren't so fine. The only other place where the atmosphere is fairly clear is in the radio range. So, and in a specific part of the radio range for radio waves between about 10 centimeters and 10 meters wavelength. What this means is if we want to do telescope observations from here on the ground, there's only a few choices: visible, some parts of the infrared, and radio. And if you're interested in resolution, you want the shortest wavelength, which puts you in the visible. But you could still do some stuff with the infrared and radio as well. If you want to do anything at any other wavelength, you need to get above the atmosphere. You need to go into space. Now, NASA does this. Quite a few countries do this. You put telescopes into space to observe at wavelengths you can't normally do so. The Hubble telescope has ultraviolet components on it because it was above the atmosphere. There are other telescopes that looked at wavelengths in the infrared we can't easily access from Earth. There are even telescopes that look for gamma rays and X-rays. And all of these instruments are great, and there are more on the way. The next big one is the JWST, which is going to be an enormous telescope that observes in the infrared. This is showing the scale of that thing relative to people. And again, here the goal is we want good resolution, but if we're going into space, that requires something big. So this entire thing has to fold up so it fits in a rocket, which is a major engineering challenge. It's basically built though now, and hopefully will be launching later this year. But this highlights one of the issues. These things are expensive and challenging to build, especially making them big enough to have sufficient resolution. Also, because they're so challenging to build, people want to use them. And there aren't many of them. So there's a lot of competition to use them. So these things are great, but they have their limitations, some of which are still mostly practical. But there's other things you can do in certain cases to use Earth-based telescopes to a bit better effect than you might think. For example, this image of the black hole, which I'm now turning into a grayscale image because that's actually what happened. That reddish color is just there for aesthetics. This is an extremely high resolution image. And so it might be natural to think that this extremely high resolution image was obtained at short visible wavelengths, because that's where it's easiest to do that thing. In practice, however, this image was not made in visible light at all. It wasn't even made in infrared light. It was made at the boundary between infrared and microwaves. The wavelength of the light used to look at this was actually 1.3 millimeters, which is 3,000 times longer than visible light. This is maybe surprising. It's like resolution is set by wavelength over diameter. Doesn't this require an enormous telescope? And the answer is yes. If you're talking about observations in the far infrared microwave region, you need big telescopes to get even decent resolution. For example, these are 10-meter class radio antennas from what is called the Karma array. These are big things. And you can see here, there's a place people could walk to give you a sense of scale. Each one of these telescopes by itself has a resolution comparable to your eye. So this sort of thing with individual scopes does not have nearly enough resolution to see the fine details we're seeing here. The thing that long wavelengths permit, though, is for you to combine data from different telescopes and treat them as if they're one gigantic telescope. And what was used to make that image is a collection of telescopes, some of which were in South America, some in North America, some in Hawaii, some in Spain, and even one in the South Pole. And basically, by combining the data from all of these different instruments in very clever ways, you can create a telescope whose effective diameter is roughly that of the Earth. Now, the way that works is by using, again, the fact that light is a wave. It's an oscillation. So as the light comes from here to here, it's not just a beam. It's an oscillation going back and forth. And your detector can measure whether it's going up or down at different times. Now, if you have a telescope down here and one up here, and you register when this one's going up and when this one's going up, those will occur at different times because they're different distances. It takes less time for the light from the red source to go this way, more time for it to go this way. So that creates a time delay in the oscillations. This one, the time delay is in the opposite direction. This ray is a longer distance than this ray. So the oscillations here occur before the oscillations here. So if you're able to do the appropriate analysis, you can actually start to pull apart objects that you couldn't otherwise do by comparing the observations made at different locations. This takes a lot of computing power and is easier to do if the wavelength of the oscillations is longer or the frequency is shorter. This kind of deep analysis is what allowed this image to be made. So all nice. So even with long wavelengths, if you can combine data from multiple telescopes, you can still get a fair amount of detail. Now, just to wrap up on this, I should say that we are no longer just getting information about distant astronomical objects from electromagnetic radiation or various forms of light. Since 2016, there have been telescopes, one of which is located in Hanford, which is fairly close by here, that can detect gravitational radiation, that can detect actually the gravity from extreme objects like merging black holes or merging neutron stars. This is a new way to look at astronomical objects, but it's kind of specialized. It's mostly used for studying black holes and neutron stars. And so we're going to hold off talking about this until we start talking about those objects. Anyway, thank you much for your time and attention, and I'll see you all in class.